Consider the invisible forces that surround you at this very moment. Electromagnetic waves carrying voices, images, and data pulse through the air at the speed of light. Your smartphone receives signals from satellites orbiting thousands of kilometers above. Radio waves from distant stars pass through your body without resistance. This invisible ocean of energy shapes every aspect of modern existence, yet it remains utterly imperceptible to human senses. We swim through electromagnetic radiation as fish swim through water, unaware of the medium that sustains our connected world. The story of how we discovered these hidden forces begins not with advanced instruments or vast laboratories, but with a young boy who dared to see beyond what eyes could perceive. Before we jump back in, tell us where you're tuning in from, and if these history tales fascinate you, make sure you're subscribed, because tomorrow I've saved something extra special for you. Edinburgh, 1850. The Royal Society's meeting chamber fills with distinguished gentlemen in dark coats, their conversations echoing off wood-panelled walls. Scientific papers await presentation, each representing years of careful observation and measurement. But today's first paper arrives under unusual circumstances. Its author, 14 years old, stands outside the chamber doors. The Society's rules are absolute. No child may address this august body. His geometric analysis of oval curves must be read by another. James Clerk Maxwell waits in the corridor while Professor James Forbes presents his work. Inside, the mathematicians listen with growing interest. This boy has discovered a method for drawing perfect ovals using pins and thread, translating physical motion into mathematical precision. The paper demonstrates insight beyond his years, yet its author cannot witness the moment. He has submitted elegant proofs about curves and geometry, but the men inside debate whether genuine understanding could emerge from someone so young. The rejection plants something deeper than disappointment. Maxwell learns early that brilliant ideas matter less than credibility, that age and appearance shape reception more than truth. This moment begins a pattern that will follow him through decades of revolutionary thinking. He will propose ideas that seem impossible, describe phenomena that instruments cannot detect, unite forces that appear separate, and repeatedly, the scientific establishment will doubt him. But understanding Maxwell's determination requires stepping back further, to the moment that shaped everything. 4 years earlier, at age 10, James stood beside his mother's deathbed. Cancer had consumed her at 48. He watched her fade, helpless against forces medicine could not explain or prevent. In that watching, something crystallized within him. The world contained mysteries. Suffering and death arrived through mechanisms hidden from direct observation. Perhaps, understanding these invisible workings might grant humanity some measure of control over fate. His father, recognizing the boy's need for purpose, encouraged his natural curiosity. At Glenlair Estate in southwestern Scotland, young Maxwell explored the countryside with urgent attention. He examined plants and insects, observed cloud formations, collected minerals. His questions cascaded without end. How do bees navigate? Why does polarized light create colors in stressed glass? What makes Saturn's rings stable? His father transcribed these inquiries in letters, amused and slightly overwhelmed by the boy's relentless wandering. The other children called him Dafty. His rural accent clashed with Edinburgh sophistication. He arrived at academy in provincial clothing that invited mockery, but Maxwell possessed something that transcended social acceptance. He saw patterns where others saw isolated facts. He recognized connections across seemingly separate phenomena. While his classmates memorized classifications, Maxwell asked why classification systems existed at all, what underlying principles might generate the diversity he observed. Mathematics became his language for invisible realities. Numbers could describe relationships that eyes could not see. Equations captured patterns that transcended specific examples. In geometry, he found shapes defined by rules rather than drawn by hand. These abstract forms possessed perfection that physical objects only approximated. A circle drawn in sand erodes with wind and tide, but the mathematical definition of a circle remains eternal, unchanged by time or decay. His fascination with light began simply, with colours. Scotland's variable weather created endless opportunities for observation. Rainbows arced across storm-cleared skies. Sunlight scattered through morning mist into separated bands of colour. But Maxwell noticed something others overlooked. The spectrum of sunlight contained every visible colour, yet human perception reduced this infinite variety to three primary sensations: red, green, and blue. This realization arrived through personal experience. Maxwell discovered he was colorblind for specific shades of red. Certain flowers appeared identical to him that others distinguished easily. This perceptual limitation became an experimental advantage. It proved that color existed in the mind as much as in light itself. External reality provided wavelengths of electromagnetic radiation. Human vision converted these wavelengths into subjective experience through three types of color-sensing cells in the retina. At Cambridge University, Maxwell designed spinning discs to test color perception. He painted discs with different proportions of primary colors, then rotated them rapidly. The spinning merged separate colors into blended perceptions. By varying proportions, he created any color sensation from just three primary sources. This demonstrated that human color vision operated through three-channel processing, not through direct perception of specific wavelengths. He photographed the same tartan ribbon through red, green, and blue filters, creating three separate black and white images. When projected together through corresponding colored lights, the images combined into a full-color picture. Maxwell had invented color photography, but more importantly, he had revealed how light's continuous spectrum could be captured through discrete channels and reconstructed into perceived reality. This insight extended beyond vision. If human perception reduced infinite wavelength variations into three-channel information, perhaps other hidden dimensions of reality existed beyond human sensory limits. Eyes detected only a narrow band of electromagnetic frequencies. What if vast ranges of invisible light surrounded us constantly? What if the visible spectrum represented merely one octave in an infinite symphony of electromagnetic waves? Maxwell's mathematics suggested exactly this. During the 1860s, working in his study at Glenlair Estate, he tackled a problem that had puzzled natural philosophers for decades. Electricity and magnetism seemed connected yet distinct. Moving magnets created electric currents. Electric currents created magnetic fields. But no one had unified these phenomena into a coherent theory. Michael Faraday had made crucial discoveries through direct experimentation. He visualized invisible lines of force surrounding magnets and electric charges. Though Faraday lacked advanced mathematics, his intuitive genius recognized that forces existed as fields filling space rather than acting instantaneously at a distance. Maxwell, reading Faraday's papers, saw mathematical beauty in these field concepts. Where Faraday described forces curving through space, Maxwell saw equations describing how field values changed from point to point. Where Faraday observed that changing magnetic fields created electric currents, Maxwell recognized mathematical relationships between rates of change. He began translating experimental observations into differential equations, mathematical statements describing how one quantity varies in relation to another. The mathematics grew increasingly complex. Maxwell filled notebooks with calculations, seeking patterns in the relationships between electric and magnetic phenomena. Existing equations described isolated effects, how charges created electric fields, how currents created magnetic fields, how changing magnetic fields induced electric currents. But these separate pieces demanded unification. Maxwell recognized that something was missing. The equations contained an asymmetry. Changing magnetic fields created electric fields, but the reverse relationship seemed incomplete. If nature truly unified these forces, then changing electric fields should create magnetic fields with equivalent elegance. He added a term to the equations, a displacement current representing how changing the electric fields generate magnetic disturbances. This addition was not derived from experiment. No instrument could detect these displacement currents directly. Maxwell added this term because mathematical symmetry demanded it, because beauty and elegance in equations often revealed physical truth. With this modification, the equations became complete. 4 statements described all electromagnetic phenomena. The first 2 described how charges create electric fields and how there are no isolated magnetic charges. The third described how changing magnetic fields create electric fields. The fourth, incorporating Maxwell's addition, described how changing electric fields and moving charges create magnetic fields. But these equations contained something extraordinary, hidden within their mathematical structure. When Maxwell manipulated them algebraically, they combined into wave equations. The equations predicted that electromagnetic disturbances propagate through space as waves, with electric and magnetic fields oscillating perpendicular to each other and to the direction of travel. More remarkable still, the equations specified exactly how fast these waves must travel. The speed emerged from 2 fundamental constants, the electric permittivity and magnetic permeability of empty space. These values had been measured in separate experiments having nothing to do with light or waves, yet when Maxwell combined them in the way his equations demanded, they produced a specific velocity, 299,792,458 meters per second. Maxwell recognized this number immediately. Astronomers had measured the speed of light through careful observations of Jupiter's moons and stellar aberrations. Their value matched Maxwell's calculation almost exactly. The implication struck him with revelatory force. Light was not a separate phenomenon. Light was an electromagnetic wave. The warmth of sunlight on skin resulted from oscillating electric and magnetic fields. The colors of the rainbow represented different frequencies of electromagnetic oscillation. Every optical phenomenon, reflection, refraction, diffraction, must obey electromagnetic laws. But the revelation extended further. If light represented electromagnetic waves at certain frequencies, then electromagnetic waves must exist at other frequencies as well. Oscillate fields faster than visible light, and you create ultraviolet radiation. Oscillate them slower, and you create infrared. Extend the spectrum further in both directions, and invisible electromagnetic waves must fill frequency ranges humans had never detected. Maxwell published these conclusions in 1865 in a paper titled A Dynamical Theory of the Electromagnetic Field. He proposed that vast regions of invisible electromagnetic radiation surrounded humanity. He predicted that devices could generate and detect these invisible waves. He unified light, electricity, and magnetism into a single theoretical framework. The scientific community's response ranged from cautious interest to outright skepticism. Lord Kelvin, Britain's most prominent physicist, declared electromagnetic waves impossible to demonstrate experimentally. Others questioned whether mathematical elegance guaranteed physical reality. Maxwell's waves existed in equations but in no laboratory. Maxwell himself never wavered in his conviction. He had followed mathematics to its logical conclusion. The equations possessed internal consistency and predictive power. They explained existing observations while forecasting new phenomena. If the mathematics was sound, nature must conform to it. But doubt gnawed at the edges of certainty. Decades passed with no experimental confirmation. Maxwell continued his work, making contributions to thermodynamics and the kinetic theory of gases. He developed statistical methods for describing molecular motion, showing how large-scale properties emerge from countless microscopic interactions. Yet the electromagnetic waves remained theoretical, mathematical ghosts, haunting empty space in equations, but invisible to instruments. In 1879, at age 48, James Clerk Maxwell died of abdominal cancer, the same disease that had taken his mother. He departed without seeing experimental proof of his greatest prediction. The invisible forces he had revealed through mathematics alone remained undetected by human senses or devices. Yet in his final years, Maxwell understood something profound about the nature of discovery. Physical reality transcends direct observation. Human senses evolved to detect threats and opportunities in the immediate environment, not to perceive all that exists. Mathematics provides vision beyond biological limits. It allows minds to explore realms where eyes cannot follow. Maxwell had used mathematics to see truly invisible forces. His equations described electromagnetic fields that filled every cubic centimeter of space, oscillating at every possible frequency. These fields carried energy and information. They connected distant regions instantaneously through field influences propagating at light speed. They represented a hidden dimension of reality as fundamental as matter itself. The boy who had been denied his voice at 14 had spoken through equations that would outlast all verbal arguments. The young man who watched his mother succumb to invisible disease had revealed invisible forces that would transform civilization. He had looked beyond the obvious and found wonder waiting in the mathematics of nature. Standing before his equations, Maxwell must have contemplated their implications with something approaching vertigo. He had unified light with forces that move compass needles and power telegraphs. He had predicted waves no one could detect. He had described an invisible ocean surrounding humanity, filled with electromagnetic radiation, spanning infinite frequencies. He could not know that within decades, invisible radio waves would carry human voices across continents and oceans. He could not imagine that his equations would enable technologies connecting billions of humans in real-time communication. He could not foresee satellites orbiting Earth, transmitting his predicted waves down to pocket devices more powerful than all of Victorian science combined. But perhaps he sensed the magnitude of his discovery. Perhaps in quiet moments at Glenlair Estate, looking across Scottish hills under endless sky, he recognized that he had glimpsed something eternal. The electromagnetic field existed before humans evolved to study it. It will persist long after humanity vanishes. Maxwell had not invented or created this hidden dimension of reality. He had simply revealed its presence through the clarity of mathematics. In this revelation lies a profound truth about discovery itself. The universe contains wonders beyond immediate perception. Invisible forces shape visible effects. The obvious represents only a fraction of what exists. And sometimes, a young mind willing to question accepted wisdom, armed with mathematics and determination, can pull back reality's curtain to reveal what was always present but never seen. Maxwell's story begins with rejection at 14 and ends with death at 48, never witnessing experimental proof. Yet between these moments, he achieved something extraordinary. He made the invisible visible, not through instruments but through equations, not through observation but through understanding. He showed that reality extends far beyond what eyes can see, and that human minds can comprehend this extended reality through the power of mathematical reasoning. The forces Maxwell revealed surround you now as you listen to these words. They carry this voice to your ears through electromagnetic waves. They connect you to information spanning the globe. They represent the foundation of modern civilization, and they began with a boy who refused to let dismissal silence his questions, who looked at light and asked what else might be hiding in frequencies beyond human perception, who dared to trust mathematics over intuition. The invisible universe awaited discovery. Maxwell found the key. But proving his revelation's reality would require another young life cut short, another tragic triumph of genius dying before witnessing the revolution it unleashed. Long before humans wondered about invisible forces, Earth itself wielded electromagnetic power on a planetary scale. 4 billion years ago, as our planet's molten iron core began its eternal rotation, something extraordinary emerged. Convection currents of liquid metal, heated by radioactive decay deep within Earth's interior, started generating a magnetic field that extended thousands of kilometers into space. This invisible shield has protected our world through geological ages, deflecting solar winds that travel at 1 million miles per hour, particles so energetic they would strip away our atmosphere without this magnetic barrier. Stand outside on any clear day and consider what surrounds you. The sun unleashes a continuous storm of charged particles, a stellar wind carrying the mass of 1 million tons per second across 93 million miles of space. These particles arrive at Earth, traveling fast enough to circle the globe in minutes. Yet you feel nothing. You breathe easily. Life persists. Because Earth's magnetic field curves around our planet like an invisible fortress, redirecting this cosmic bombardment around us, creating a protective bubble called the magnetosphere that extends 60,000 kilometers toward the Sun. Without this ancient electromagnetic guardian, Earth would resemble Mars. The red planet lost most of its magnetic field billions of years ago when its core cooled and solidified. Solar wind gradually stripped away the Martian atmosphere, transforming a world that once held liquid water and possibly life into a frozen desert. Earth's magnetic field, sustained by our planet's churning metallic heart, has preserved the thin envelope of air and water that makes our existence possible. For nearly all of human history, we remained unaware of this protection. Our ancestors looked upward at stars and planets, tracked seasons and tides, but never suspected that invisible forces surrounded them. The first hint arrived through lodestone, chunks of naturally magnetized iron ore that pointed persistently toward Earth's northern regions. Chinese navigators recognized lodestone's peculiar properties more than 2,000 years ago. They carved these magnetic rocks into spoon shapes, balancing them on smooth bronze plates. The spoon's handle would swing to point south, regardless of how many times they turned the plate. This mysterious attraction seemed magical, as if stones could sense direction through some hidden awareness. But generations of sailors learned to trust these pointing stones, using them to maintain course when clouds obscured stars. The Chinese called these devices south-pointing fish when they floated magnetized needles in water bowls. By the 11th century, maritime explorers carried these compasses on ships venturing beyond sight of land. The magnetic needle provided direction with unwavering consistency, as if it knew something about Earth's geometry that human senses could not perceive. European sailors adopted magnetic compasses by the 13th century, transforming ocean navigation. Ships could maintain bearing through storms and fog. Explorers could chart courses across open ocean, trusting the needle's indication even when utterly lost. Magellan's circumnavigation, Columbus's Atlantic crossing, every age of exploration depended on magnetism's invisible guidance. Yet no one understood why lodestone pointed north. Theories ranged from magnetic mountains at Earth's poles to celestial influences from the North Star. The true explanation, that Earth itself was a giant magnet with field lines emerging from its southern hemisphere and converging at the north, remained beyond imagination. William Gilbert, physician to Queen Elizabeth I, performed systematic experiments with magnetism in the late 1500s. He carved spherical lodestones and mapped how compass needles oriented around them at different positions. These miniature magnetic globes, which Gilbert called terrellas, or little earths, produced patterns matching compass behavior at different latitudes. Gilbert proposed that Earth itself was a vast magnet, and compass needles aligned with planetary field lines. This insight represented a profound shift in thinking. Earth was not just a platform for human activity, but an active participant in invisible physical processes. Our planet generated forces that extended into surrounding space, forces that guided needles and influenced the cosmos beyond our atmosphere. But magnetism remained mysterious despite Gilbert's insights. No one knew what caused magnetic attraction or how lodestone acquired its properties. The force seemed fundamental yet unexplained, acting through empty space without apparent mechanism. Then lightning revealed another hidden force. Thunderstorms have terrified and fascinated humans throughout history. Electrical discharge tears through air, releasing energy in blinding flashes and deafening thunder. Ancient observers recognized lightning's destructive power, but attributed it to divine anger rather than natural processes. Benjamin Franklin, the American polymath, suspected otherwise. In 1752, he performed his famous kite experiment during a Philadelphia thunderstorm. He flew a kite with a metal key attached to the string's base, allowing electrical charge from storm clouds to flow down the wet hemp fibers. When he brought his knuckle near the key, sparks jumped through air, with a crackling snap. Franklin had captured electricity from the sky. He had demonstrated that lightning and the static sparks produced by rubbing amber against cloth were fundamentally the same phenomenon occurring at vastly different scales. A storm cloud might discharge 800 million volts through a single lightning bolt, carrying 30,000 amperes of current and heating air to 30,000 degrees Celsius in milliseconds. Yet this awesome display of power operated through the same principles as tiny sparks hopping between fingers and doorknobs. Franklin's lightning rod invention followed naturally from this understanding. By placing pointed metal conductors atop buildings and connecting them to ground through cables, he provided a low-resistance path for electrical discharge. Lightning struck the rods preferentially, following the path of least resistance harmlessly into earth rather than exploding through wooden structures. Franklin had not merely discovered a natural phenomenon, but had learned to channel and control it. Yet electricity remained separate from magnetism in scientific thinking. Both involved invisible forces, both could attract and repel, but they seemed distinct phenomena governed by different laws. No one suspected the deep connection between them. That changed in 1820 during a lecture at the University of Copenhagen. Hans Christian Ørsted, demonstrating electrical current from a voltaic pile, noticed something peculiar. He had placed a compass near the wire, conducting electricity. As current flowed, the compass needle deflected, swinging perpendicular to the wire, cut the current, and the needle returned to pointing north. Restore the current, and the needle swung aside again. Ørsted recognized immediately that he had witnessed something profound. Electric current created magnetic effects. The two forces were not separate but connected. A wire carrying electrons in motion generated a magnetic field in the first, surrounding space, strong enough to overpower Earth's magnetic influence on the nearby compass. This discovery electrified the scientific community. Within weeks of Ørsted's publication, researchers across Europe began investigating electricity-magnetism connections. André-Marie Ampère in France demonstrated that parallel wires carrying current in the same direction attracted each other, while currents flowing in opposite directions caused repulsion. He derived mathematical laws describing the magnetic forces between current-carrying conductors, but the deepest insights came from Michael Faraday in England. Faraday, born to poverty and largely self-educated, possessed intuitive genius for envisioning physical processes. He thought in images and patterns rather than mathematical abstractions. Where others saw isolated phenomena, Faraday saw unified field structures. In 1831, Faraday performed an experiment that would transform civilization. He wrapped two separate coils of wire around an iron ring. When he connected one coil to a battery, completing the circuit and allowing current to flow, he observed that a momentary current appeared in the second coil, even though the two circuits had no direct connection. The effect lasted only while current in the first coil was changing, either starting or stopping. Faraday recognized what was happening. The first coil's current created a magnetic field through the iron ring. This changing magnetic field induced an electric current in the second coil. He had discovered electromagnetic induction, the process by which changing magnetic fields generate electric currents. This was the reverse of Ørsted's discovery. Ørsted had shown that electric current creates magnetism. Faraday revealed that changing magnetism creates electricity. The implications were staggering. Mechanical motion could be converted to electricity. Faraday built the first electric generator by rotating a copper disc between the poles of a horseshoe magnet. As the disc spun, cutting through magnetic field lines, electric current flowed from the disc's center to its edge. Mechanical rotation had become electrical energy. Faraday called these devices electrical machines, but we know them as generators and motors. Every power plant on Earth, whether driven by falling water, burning coal, nuclear fission, or wind, operates through electromagnetic induction. Turbines spin massive coils of wire through magnetic fields, generating the alternating current that flows through power grids to billions of devices. Faraday's iron ring experiment in a London laboratory basement had revealed the principle that would illuminate cities and power industries. But Faraday contributed something deeper than practical devices. He developed the concept of field itself. Rather than imagining forces acting instantaneously across empty space, Faraday visualized invisible lines of force filling the region around magnets and electric charges. These lines had physical reality, he insisted. They represented actual conditions in space, not merely convenient mathematical descriptions. He demonstrated field reality through iron filings scattered on paper placed over a magnet. The filings aligned along curves connecting the magnet's poles, making field lines visible. The pattern existed, whether filings revealed it or not. Space itself possessed structure imposed by electromagnetic fields. This field concept troubled mathematical physicists who preferred action at a distance formulations. How could empty space contain structure? What physical substance composed these fields? Faraday lacked advanced mathematics to formalize his insights, but he knew with absolute certainty that fields were real. He had felt their effects, mapped their geometries, observed their behaviors under countless conditions. Consider what Faraday was proposing. Every magnet, every electric charge, every current-carrying wire creates invisible alterations in surrounding space. These alterations extend outward at finite speed, filling regions with field values that determine forces on other charges and currents. The universe contains not just matter moving through empty space, but matter embedded in fields, with the fields themselves possessing energy and momentum. This was revolutionary thinking. It suggested that apparently empty space was filled with invisible structure, that the vacuum itself could vibrate and carry energy. It implied that electromagnetic effects propagated through space at finite speed rather than acting instantaneously, and it meant that understanding electromagnetism required understanding fields as fundamental entities. Faraday's papers, filled with experimental descriptions and field visualizations but lacking mathematical rigor, frustrated some colleagues while inspiring others. Lord Kelvin translated Faraday's verbal descriptions into mathematical language, but even Kelvin never fully embraced the field theory's implications. The person who would carry Faraday's insights to their logical conclusion was studying at Cambridge during these years, reading Faraday's papers with growing fascination. James Clerk Maxwell recognized in Faraday's work the physical intuition his mathematical genius could formalize. Where Faraday described field lines and flux, Maxwell saw differential equations describing spatial variations. Where Faraday observed induction and noticed symmetries, Maxwell recognized mathematical relationships demanding completion. The two men, one from poverty with no formal training, one from privilege with advanced mathematics, complemented each other perfectly across a generation. By the 1860s, several pieces had fallen into place. Electricity and magnetism were connected, two aspects of electromagnetic force. Changing magnetic fields created electric currents. Electric currents created magnetic fields. Fields possessed physical reality as structures in space. And underlying all these phenomena were quantitative relationships, waiting for proper mathematical expression. But one crucial observation had not yet been made. No one had detected electromagnetic waves propagating through space. Ørsted's magnetic effects appeared instantaneously when current flowed. Faraday's induced current seemed to arise the moment magnetic flux changed. If fields propagated at finite speed, the delays were too small to measure with available instruments. Maxwell's equations predicted these waves should exist and specified their speed precisely. But prediction and detection were different matters. The waves might be real yet undetectable, mathematical ghosts haunting equations but never manifesting in laboratories. For electromagnetic wave theory to transform from speculation to established science, someone would need to generate and detect these invisible oscillations experimentally. That would require new techniques and new thinking. It would require building devices that oscillated at rates far faster than any mechanical apparatus. It would require detection methods sensitive enough to capture waves carrying tiny amounts of energy. And it would require a brilliant young experimenter willing to test Maxwell's seemingly impossible predictions. But before that crucial experiment, before electromagnetic waves were proven real, humanity had already begun harnessing electromagnetic forces for practical purposes. Telegraph systems spanned continents, sending messages as pulses of electric current through copper wires. Undersea cables crossed the Atlantic, connecting Europe and America with electromagnetic signals that traveled thousands of miles in seconds. Electric motors drove machinery with unprecedented efficiency. Yet all these applications used electromagnetic forces in wires and circuits. They demonstrated that electricity and magnetism could be controlled and utilized, but they did not reveal the deeper truth that Maxwell had uncovered. They did not show that electromagnetic disturbances could propagate through empty space as waves, carrying energy and information without any physical medium. The ancient forces that had protected Earth for billions of years, that had guided compass needles for thousands of years, that lightning had revealed and Franklin had captured, remained only partially understood. Humanity had learned to generate electricity, to create magnetic fields, to induce currents and spin motors. We had awakened to electromagnetic power's practical utility, but the electromagnetic spectrum's full extent, the invisible waves filling space at every frequency, the unification of light and electromagnetic oscillation, all this awaited experimental confirmation. Maxwell had seen it mathematically. Faraday had intuited it physically. But seeing and intuiting are not proving. The proof would come from Germany, from another young physicist racing against time, building apparatus in a darkened laboratory to catch evidence of waves that existed, if at all, only in Maxwell's elegant equations. The ancient forces were awakening to human understanding, but their deepest secrets still required one more revelation, one final experimental triumph that would arrive too late for the man who predicted it, and would not fully blossom even for the man who confirmed it. The electromagnetic revolution was beginning, but no one yet realized how completely it would transform human civilization. In his study at Glenlair Estate, surrounded by Scottish countryside that had nurtured his curiosity since childhood, James Clerk Maxwell confronted a mathematical puzzle that had consumed him for years. Papers covered his desk, filled with equations describing electric and magnetic phenomena. Some described how electric charges create fields radiating outward through space. Others captured how magnetic poles generate their own field patterns. Still others mathematically expressed Faraday's, the discovery that changing magnetic fields induce electric currents, and Ampere's observation that moving charges create magnetism. Maxwell sought unity. These separate equations described related phenomena, pieces of a larger picture he could sense but not yet see completely. The mathematics felt incomplete, asymmetric. Nature rarely produces fundamental laws, lacking elegance and balance. Yet the existing equations possessed an troubling one-sidedness. Consider the asymmetry that bothered Maxwell. Faraday had shown that a changing magnetic field creates an electric field. This was induction, the principle powering generators and transformers. The mathematics captured this beautifully. Take the rate of change of magnetic field through any closed loop, and it equals the electric field circulating around that loop. Elegant, clear, experimentally verified. But what about the reverse? If changing magnetism creates electricity, shouldn't changing electricity create magnetism? Ampere's law described how steady electric currents generate magnetic fields, but it said nothing about what happens when electric fields themselves change over time. The equations were not symmetric. They did not possess the mathematical balance that typically signals deep physical truth. Maxwell made a bold decision. He would add a term to the equations, a displacement current representing how changing electric fields generate magnetic effects just as changing magnetic fields generate electric effects. This was not forced by experimental observation. No instrument could detect displacement currents directly. Maxwell added this term because mathematics demanded it, because symmetry required it, because beauty in equations often preceded experimental confirmation. With this addition, everything changed. The equations became complete, balanced, symmetric. 4 statements now described all electromagnetic phenomena. First, electric charges create electric fields that radiate outward, with field strength decreasing by the square of distance. Second, magnetic field lines always form closed loops, never beginning or ending at isolated magnetic charges because magnetic monopoles do not exist. Third, changing magnetic fields create circulating electric fields, the essence of induction. Fourth, electric currents and changing electric fields create circulating magnetic fields. These 4 equations, written in modern vector notation, occupy just a few lines, yet they contain within their mathematical structure the complete description of electromagnetic behavior. Every electric motor, every radio wave, every beam of light, every electromagnetic phenomenon in the universe obeys these 4 statements. They represent one of physics' greatest achievements, comparable to Newton's laws of motion or Einstein's relativity. But Maxwell discovered something extraordinary hidden within these equations. When he manipulated them algebraically, combining and rearranging terms, they transformed into wave equations. The mathematics predicted that electromagnetic disturbances would propagate through space as waves, with electric and magnetic fields oscillating perpendicular to each other and to their direction of travel. Imagine the moment of realization. Maxwell, working through pages of algebra, suddenly recognized the wave equation emerging from his electromagnetic expressions. These were not just any waves, but waves with a specific, predicted velocity determined entirely by electromagnetic constants. The wave speed depended on 2 fundamental quantities: epsilon 0, the electric permittivity of free space, measuring how easily electric fields form in vacuum, and mu 0, the magnetic permeability of free space, measuring how easily magnetic fields form. These constants had been measured in laboratory experiments, having nothing whatsoever to do with light or wave propagation. They came from static electricity experiments and magnetic force measurements. Yet when Maxwell combined these values according to his wave equation, calculating 1 divided by the square root of their product, the result was a specific velocity, 299,792,458 meters per second. Maxwell knew this number. Astronomers had measured light's speed through observations of Jupiter's moons, timing how eclipse schedules shifted as Earth's distance from Jupiter varied. They had measured it through stellar aberration, the apparent shift in star positions caused by Earth's orbital motion combined with light's finite speed. These astronomical measurements yielded a value matching Maxwell's calculation with remarkable precision. The conclusion was inescapable. Light was an electromagnetic wave. The warmth you feel from sunlight results from oscillating electromagnetic fields. The colors your eyes perceive are different frequencies of electromagnetic oscillation. Red light oscillates at 430 trillion cycles per second. Violet light at 750 trillion cycles per second. The entire visible spectrum, every shade and hue, represents electromagnetic waves at different frequencies. This discovery unified phenomena that had seemed completely separate. Optics, the science of light, became a subset of electromagnetism. Every observation about reflection and refraction, every experiment with lenses and prisms, every theory about light's behavior now fell under electromagnetic laws. The equations that described compass needles and electric circuits also described rainbows and sunsets, but the implications extended far beyond unifying light with electromagnetism. If visible light represented electromagnetic waves at certain frequencies, then electromagnetic waves must exist at frequencies humans cannot see. Oscillate the fields faster than violet light, and you create ultraviolet radiation. Oscillate them slower than red light, and you create infrared. Continue the progression, and the electromagnetic spectrum extends infinitely in both directions. Maxwell recognized that humanity was blind to most of the electromagnetic spectrum. Human eyes evolved to detect a narrow frequency band where the sun's radiation peaks, the wavelengths most useful for seeing surfaces and objects in sunlight. But vast ranges of electromagnetic radiation remained invisible, filling space undetected. He predicted that devices could generate these invisible waves, oscillate electric charges back and forth rapidly, and they should radiate electromagnetic energy at the oscillation frequency. He predicted that other devices could detect these waves. A receiving antenna should experience induced currents when electromagnetic waves pass through it, just as compass needles respond to magnetic fields. Maxwell published these revolutionary conclusions in 1865 in his paper, A Dynamical Theory of the Electromagnetic Field. The work represented mathematical physics at its most powerful. Starting from experimental observations about electricity and magnetism, adding one term demanded by mathematical symmetry, Maxwell had derived the wave nature of light, unified optics with electromagnetism, predicted invisible radiation spanning infinite frequencies, and specified the exact speed at which all these waves travel. Yet, experimental confirmation remained elusive. The waves existed in Maxwell's mathematics, but in no laboratory. The predicted speed matched light's measured speed, strongly suggesting Maxwell's theory was correct. But suggestion and proof are different standards. Science demands that theoretical predictions face experimental test. The challenge was formidable. To generate electromagnetic waves, you needed oscillating electric charges, but mechanical oscillations were far too slow. Even a tuning fork vibrating at 1,000 cycles per second produces frequency far below visible light. Maxwell's theory predicted that Electromagnetic waves should exist at all frequencies, but generating them required oscillators operating at millions or billions of cycles per second, rates impossible with any mechanical device. Detection presented equal challenges. An antenna would need to respond to oscillating fields carrying tiny amounts of energy. The receiver would need extraordinary sensitivity to detect signals from the first primitive transmitters. And all this required someone willing to invest years in experimental work testing predictions that many physicists considered unprovable. Maxwell himself attempted no such experiments. His genius lay in theoretical insight, not experimental apparatus. He trusted his mathematics completely and felt no need for experimental proof to convince himself. The equations were correct, he knew. Nature would confirm them eventually, but others doubted. Lord Kelvin, Britain's most eminent physicist, dismissed electromagnetic waves as mathematical artifacts. The equations might be elegant, but that did not guarantee physical reality. Kelvin argued that Maxwell's displacement current term was unnecessary complication, that the simpler equations without this addition were sufficient. He declared electromagnetic wave generation and detection impossible in practice. This was not mere skepticism, but reasoned doubt from accomplished scientists. Maxwell's theory required accepting that empty space could vibrate, that vacuum possessed physical properties allowing wave propagation. It required imagining that changing electric fields created real physical effects, even with no charges present. It demanded faith in mathematical beauty as a guide to physical truth. Maxwell faced this doubt with calm certainty. He had followed mathematics where it led, trusting that proper equations revealed reality. The displacement current was not arbitrary addition but necessary completion. The wave equation was not mathematical coincidence but profound physical prediction. Light's speed emerging from electromagnetic constants was not numerical accident but nature revealing deep unity. In 1879, James Clerk Maxwell died at 48, the same age his mother had died. Abdominal cancer consumed him, just as it had consumed her. He departed having revolutionized physics, having unified major branches of science, having predicted phenomena no one had detected, but he died without witnessing experimental confirmation of electromagnetic waves. His equations survived him. They were published, studied, debated, but not yet proven. For 8 years after Maxwell's death, electromagnetic waves remained mathematical predictions. The greatest unification in physics rested on faith in equations rather than experimental evidence. But the mathematics was correct. The waves were real. And someone was preparing to prove it, working in a German laboratory with spark gaps and wire loops, about to catch the invisible oscillations Maxwell had described. The proof was coming. The electromagnetic spectrum was about to reveal itself, and the revolution Maxwell predicted was about to begin, though he would never witness it, and the man who confirmed it would never see how completely it would transform human civilization. 4 equations containing infinite implications, mathematical symmetry revealing physical truth, theoretical prediction awaiting experimental confirmation. Maxwell had opened the door to the invisible spectrum. Now someone needed to walk through it, to make the waves manifest, to demonstrate that mathematics had revealed reality rather than invented fantasy. The electromagnetic universe was waiting, hidden in frequencies beyond human perception, ready to emerge from theory into technology, from prediction into civilization-transforming power. Heinrich Hertz was born in 1857, the same year Maxwell began formulating his electromagnetic field theory. By the time Hertz entered university in Hamburg, Maxwell's equations were published but unproven, mathematical predictions floating in theoretical space without experimental anchor. The young Hertz showed exceptional talent in both mathematics and laboratory work, a rare combination that would prove essential for the task awaiting him. He studied under Hermann von Helmholtz in Berlin, one of the few physicists who took Maxwell's wave prediction seriously. Helmholtz recognized that if electromagnetic waves existed, they represented the most important unconfirmed prediction in physics. He encouraged his students to attempt detection, even offering prize money for successful experimental demonstration. But year after year, no one succeeded. The waves, if they existed at all, remained beyond reach of available techniques. The challenge seemed insurmountable. To generate electromagnetic waves, you needed oscillating electric charges at high frequencies. But how do you make charges oscillate millions of times per second? Mechanical devices were useless at such speeds. Electric currents alternating in wires might work, but generating and controlling such rapid oscillations exceeded existing technology. And even if you somehow created the waves, how would you detect them? What instrument could register oscillating electromagnetic fields carrying infinitesimal energy? Hertz pondered these problems throughout the 1880s. He taught physics at the Technical University of Karlsruhe, conducting experiments in a modest laboratory. Other physicists had abandoned the search for electromagnetic waves as impractical. Lord Kelvin's declaration that they were impossible to demonstrate had discouraged many researchers. Maxwell was dead. His theory, however elegant, might be wrong. Perhaps electromagnetic waves were mathematical fantasy, artifacts of equations that did not correspond to physical reality. But Hertz could not abandon the question. The mathematics was too beautiful. Maxwell's unification of light and electromagnetism was too profound. If the theory was correct, electromagnetic waves had to exist. They could not hide forever. Some experimental arrangement, some combination of apparatus, should catch them. The breakthrough came from understanding how sparks behave. When high voltage discharges across a gap between metal spheres, it creates a spark, a brief surge of current as charge flows through ionized air. Hertz realized that this current surge was not smooth but oscillatory. The charge rushed across the gap, overshot equilibrium, rushed back, overshot again, creating rapid oscillations at frequencies determined by the circuit's electrical properties. These oscillations were fast, millions of cycles per second, fast enough perhaps to generate electromagnetic waves at detectable frequencies. If Hertz could create a circuit that oscillated at the right frequency when sparked, and if he could build a detector sensitive enough to respond to the radiated waves, he might catch Maxwell's predicted radiation. He constructed a transmitter from a simple loop of wire with a small gap between its ends. By charging this loop to high voltage and allowing it to discharge across the gap, he created oscillating currents at frequencies around 50 million cycles per second. The circuit was not sophisticated, just thick copper wire bent into a rectangle with two metal spheres nearly touching at one point. But when it sparked, electric charge surged back and forth through the loop at extraordinary speed. If Maxwell was correct, this oscillating current should radiate electromagnetic energy. The waves should spread outward from the loop at the speed of light, carrying oscillating electric and magnetic fields perpendicular to their direction of travel. And somewhere in the laboratory, a suitable detector should respond to these invisible oscillations. Hertz built his detector from an even simpler apparatus, a circular loop of wire with a tiny gap between its ends. This receiving loop was not connected to any voltage source. It sat across the room from the transmitter, seemingly inert. But Hertz reasoned that if electromagnetic waves passed through this loop, they should induce oscillating currents, just as Faraday's changing magnetic fields induced currents in conducting loops. And if the induced currents were strong enough, they might produce tiny sparks across the detector's gap. In 1886, in his laboratory at Karlsruhe, Hertz sparked his transmitter and watched his detector. Across several meters of apparently empty space, tiny sparks appeared in the detector gap. They were barely visible, requiring a darkened room to observe clearly, but they were unmistakable. When the transmitter sparked, the detector sparked. When Hertz moved the detector farther away, the sparks weakened. When he brought it closer, they strengthened. Hertz had generated and detected electromagnetic waves. Maxwell's 20-year-old prediction was confirmed. The invisible radiation existed exactly as the equations described. Electromagnetic waves propagated through space at the speed of light, just as Maxwell had calculated from electromagnetic constants. But Hertz did not stop with simple detection. He was an experimental physicist of the highest caliber, and he recognized that confirming electromagnetic waves' existence was not enough. He needed to demonstrate that these waves possessed properties Maxwell's equations predicted. He needed to show they could be reflected, refracted, polarized, and made to interfere, just like light waves. Over the next 2 years, Hertz performed a series of brilliant experiments. He built a large metal sheet and placed it behind his detector. The electromagnetic waves reflected off the metal, bouncing back toward the transmitter. When reflected, waves met newly transmitted waves traveling in opposite directions. They created standing wave patterns. Hertz moved his detector through these patterns, finding positions where waves reinforced each other producing strong signals, and positions where waves cancelled producing no signal. The distance between these positions allowed him to measure the wavelength precisely. He calculated wave speed by multiplying wavelength times frequency. His oscillator operated at approximately 50 million cycles per second. The wavelength measured about 6 meters. Multiply them together. 50 million times 6 equals 300 million meters per second. Within experimental uncertainty, this matched the speed of light. Maxwell's prediction was confirmed quantitatively, not just qualitatively. Hertz demonstrated that electromagnetic waves could be focused using curved metal reflectors, just as light focuses using curved mirrors. He showed that they polarized, meaning their electric field oscillations could be oriented in specific directions. He passed them through large prisms made of pitch, demonstrating refraction analogous to light bending through glass. Every optical phenomenon had its electromagnetic equivalent at radio frequencies. Perhaps most remarkably, Hertz showed that his electromagnetic waves and visible light were fundamentally identical, differing only in frequency. Light oscillates at hundreds of trillions of times per second. Hertz's waves oscillated at millions of times per second. But both were electromagnetic radiation, both propagated at the same speed. Both obeyed Maxwell's equations. The electromagnetic spectrum was real, continuous, extending from the lowest frequencies to the highest. The scientific community's response was immediate and enthusiastic. Lord Kelvin, who had declared electromagnetic waves impossible to demonstrate, graciously acknowledged Hertz's success. Physicists worldwide recognized that Maxwell's theory had passed the crucial test. The equations were not just elegant mathematics, but accurate descriptions of physical reality. Electromagnetic waves existed, they could be generated and detected, and they behaved exactly as Maxwell predicted. Yet Hertz himself remained curiously unmoved by his discovery's implications. When asked about practical applications of electromagnetic waves, he replied that they had none, that this was purely scientific research, increasing human knowledge without practical utility. He could not imagine that his laboratory demonstration would transform human civilization within decades. This was not short-sightedness, but honesty about his own interests. Hertz was a pure researcher, fascinated by fundamental questions about nature. He had proven Maxwell correct. He had demonstrated electromagnetic wave properties. He had expanded human understanding of the physical world. These achievements satisfied him completely. What engineers or inventors might do with this knowledge was not his concern, but fate would not grant Hertz time to see even the first practical applications. In 1892, at age 35, he began experiencing severe headaches and facial pain. Doctors initially dismissed his symptoms as minor ailments, but the pain intensified. By 1893, his condition was diagnosed as Wegener's granulomatosis, a rare disease causing inflammation and tissue damage throughout the body. The disease progressed rapidly. Hertz's face swelled grotesquely. His nasal passages became blocked. Infections spread through his sinuses and into his skull. Despite multiple surgeries and the best medical care available, nothing stopped the disease's advance. On January 1st, 1894, Heinrich Hertz died. He was 36 years old. He departed having confirmed the century's most important theoretical prediction. He had demonstrated that invisible electromagnetic waves filled the universe at every frequency. He had shown that human technology could generate and detect radiation beyond the visible spectrum. He had opened the electromagnetic spectrum to human exploration and exploitation. But he died never imagining radio broadcasting, never conceiving wireless telegraphy, never dreaming that electromagnetic waves would carry voices across continents and oceans. He died before Marconi's first radio transmission, before the first wireless telegraph message, before anyone recognized that his laboratory curiosity would become the foundation of global communication. Consider the tragic pattern emerging. Maxwell predicted electromagnetic waves through pure mathematics but died at 48, never witnessing experimental confirmation. Hertz confirmed their existence through brilliant experiments but died at 36, never seeing practical applications. Two young geniuses, both crucial to humanity's electromagnetic awakening, both departed before their discoveries transformed civilization. Yet their work endured. Maxwell's equations remained valid, describing electromagnetic phenomena with perfect accuracy. Hertz's experimental techniques provided templates for future radio. Technology. The electromagnetic spectrum they revealed awaited exploitation by inventors and engineers who would recognize what pure scientists had overlooked: that invisible waves could carry information across any distance at the speed of light. In 1895, just 1 year after Hertz's death, Guglielmo Marconi read about his experiments and immediately grasped their commercial potential. If electromagnetic waves could cross a laboratory, why not cross a town? Why not cross the ocean? Marconi began building more powerful transmitters and more sensitive receivers. He extended transmission distances from meters to kilometers, from kilometers to hundreds of kilometers. By 1899, Marconi transmitted messages across the English Channel. Ships at sea received wireless signals from shore stations. The maritime industry recognized that electromagnetic waves could save lives, allowing ships in distress to call for help without visual or sound signals limited to a few kilometers range. But many physicists insisted that radio waves, like light, traveled in straight lines and could not follow Earth's curvature. Transmission distances were limited by the horizon, they argued. Ships might communicate with nearby shore stations, but long-distance wireless telegraphy was impossible. Radio waves would shoot off into space rather than bending around the planet. Marconi disagreed. In 1901, he attempted what experts declared impossible: wireless transmission across the Atlantic Ocean. He built a powerful transmitter in Cornwall, England, capable of generating electromagnetic waves at frequencies of a few 100,000 cycles per second. He travelled to Newfoundland, Canada, and set up a receiving antenna, a wire suspended from a kite flying in winter winds. On December 12, 1901, Marconi listened through primitive earphones as his assistant in England transmitted the letter S in Morse code, 3 dots, across 3,000 kilometers of ocean. Through what experts said was impossible distance for radio waves, Marconi heard the signal. ... Clear, unmistakable, repeated at scheduled intervals. Electromagnetic waves had crossed the Atlantic. Marconi had proven the skeptics wrong, though he did not yet understand how. Radio waves do not simply shoot off into space, but reflect off the ionosphere, a layer of charged particles in the upper atmosphere. This ionospheric reflection allows radio waves to follow Earth's curvature, bouncing between ground and sky across continental and oceanic distances. Marconi discovered this capability through experiment, while the theoretical explanation came later. The wireless age had begun. Within years, radio stations sprouted across continents. Ships carried wireless equipment as standard safety apparatus. Military forces recognized electromagnetic waves' strategic value for communication. Commercial interests saw profit in broadcasting news, entertainment, and advertising. Maxwell had predicted it mathematically. Hertz had proven it experimentally. Marconi had demonstrated it practically. And now electromagnetic waves were escaping human control, proliferating across the spectrum, filling space with signals carrying information at light speed. But both Maxwell and Hertz missed witnessing this revolution. They worked in isolation from practical concerns, driven by curiosity about fundamental nature rather than technological application. They revealed the electromagnetic spectrum without imagining its civilization-transforming power. They died young, their work complete scientifically, but not yet realized technologically. Their legacy was equations and experiments, mathematical frameworks and laboratory techniques. But from these foundations, others would build global communication networks, broadcasting systems, radar, television, satellite links, wireless internet, the entire electromagnetic infrastructure of modern life. 20 years of doubt between prediction and proof, then 8 years more before practical applications, then an explosive century of electromagnetic innovation that continues accelerating. Maxwell and Hertz opened the door to the invisible spectrum. The electromagnetic revolution was beginning, though its pioneers would never witness what they had unleashed. The 20th century opened with electromagnetic waves spreading across the planet. What began as Maxwell's mathematical prediction and Hertz's laboratory curiosity became humanity's nervous system, connecting distant points with invisible signals traveling at the speed of light. Within decades, electromagnetic radiation would reshape human civilization more profoundly than any technology since the printing press. Marconi's transatlantic signal in 1901 proved that wireless communication could span oceans, but many observers dismissed this as a curiosity for maritime use, perhaps useful for ships but irrelevant to most people's lives. They could not imagine electromagnetic waves entering homes, carrying voices and music, transforming information distribution from physical transport to instantaneous broadcast. The first radio stations emerged in the early 1920s. On November 2nd, 1920, Pittsburgh's KDKA broadcast the Harding-Cox presidential election returns. About 1,000 receivers captured the signal. People gathered around primitive radio sets, listening through crackling static as electromagnetic waves carried human voices directly into their homes. The broadcast lasted several hours, announcing election results as telegraph messages arrived at the studio. This was revolutionary, not merely as technology, but as social transformation. For the first time in human history, information could reach vast audiences simultaneously without physical distribution. No newspapers to print and deliver, no messengers to dispatch, no physical objects moving through space, just electromagnetic waves radiating outward from transmitting antennas, carrying modulated signals that receivers decoded into sound. By 1930, millions of families owned radios. President Franklin Roosevelt's fireside chats reached the entire nation simultaneously. People in California heard his voice at the same instant as people in New York, all receiving the same electromagnetic waves transmitted at the same moment. National consciousness emerged from this simultaneous shared experience, the sense that millions participated in the same event despite geographic separation. But radio was merely the beginning. Electromagnetic waves could carry not just sound but images. Television technology, developed through the 1920s and 30s, encoded visual information into electromagnetic signals. By the 1950s, television sets appeared in homes across developed nations. People watched events unfold in real time through electromagnetic waves carrying 60 images per second into their living rooms. On July 20th, 1969, 600 million people watched astronauts walk on the moon's surface. The images traveled 238,900 miles from lunar surface to Earth, electromagnetic waves carrying humanity's greatest adventure across empty space. Those waves, predicted by Maxwell and demonstrated by Hertz, now connected Earth to other celestial bodies, making humanity witness to footsteps on another world. Consider what this meant. Electromagnetic waves, invisible and imperceptible to human senses, had become humanity's primary information carrier. Everything people knew about distant events arrived through electromagnetic radiation. News, entertainment, education, all flowed through the spectrum Maxwell had revealed mathematically, and Hertz had confirmed experimentally. The electromagnetic spectrum became crowded. Radio stations broadcast at frequencies from 500 kHz to 100 MHz. Television occupied frequencies from 50 to 900 MHz. Governments divided the spectrum into licensed bands, creating regulatory frameworks to prevent signals from interfering with each other. The invisible ocean of electromagnetic radiation became property, bought and sold, regulated and controlled. Military applications drove rapid development. Radar systems, developed during World War II, used electromagnetic waves to detect aircraft and ships at distances exceeding 100 kilometers. A transmitter sent pulses of high-frequency electromagnetic radiation. When these pulses struck metal objects, they reflected back toward the transmitter. Receivers detected these reflections, measuring the time delay between transmission and reception to calculate distance with precision. Radar could see through clouds and darkness, detecting targets invisible to human eyes. It provided early warning of incoming bombers, guided anti-aircraft fire, and helped ships navigate through fog. The electromagnetic spectrum had become not just a communication medium, but a sensing tool, revealing distant objects through their electromagnetic reflections. After the war, radar technology found civilian applications. Weather forecasting improved dramatically as radar revealed storm systems hundreds of kilometers away. Air traffic control used radar to track aircraft positions, preventing collisions and managing increasingly crowded skies. Ships navigated safely through fog using radar to detect coastlines and other vessels. But the most profound transformation came with satellite technology. In 1957, the Soviet Union launched Sputnik, humanity's first artificial satellite. This metal sphere, smaller than a beach ball, orbited Earth transmitting simple radio signals. Those signals announced that humanity had escaped planetary confinement, that we could place technology in orbit and communicate with it through electromagnetic waves. Satellite capabilities expanded rapidly. Communication satellites, positioned in geostationary orbit, 35,786 kilometers above Earth's equator, remained fixed over specific locations. Signals transmitted to these satellites reflected back to Earth across entire hemispheres. Transatlantic telephone calls, once requiring expensive undersea cables, now traveled through space via satellite relay. Television broadcasts reached global audiences through satellite distribution networks. Navigation satellites revolutionized positioning and timekeeping. The Global Positioning System, developed by the United States military and later opened for civilian use, consists of at least 24 satellites orbiting at altitudes of 20,184 kilometers. These satellites continuously broadcast electromagnetic signals containing precise timing information from atomic clocks. Your smartphone receives signals from multiple GPS satellites, simultaneously. By measuring tiny differences in signal arrival times, it calculates your position anywhere on Earth to within a few meters. This requires extraordinary precision. The satellites travel at 14,000 kilometers per hour. Their atomic clocks measure time to nanosecond accuracy, and all of it depends on electromagnetic waves traveling at exactly the speed Maxwell calculated from electromagnetic constants. Mobile phones transformed human connection again. The first cellular networks emerged in the 1980s, dividing geographic areas into cells served by local transmitters. As you move through the landscape, your phone switches seamlessly between cells, maintaining connection through electromagnetic signals. By 2025 billion people owned smartphones, devices that communicate via electromagnetic waves at frequencies around 2.4 GHz, sending and receiving data continuously. Think about what surrounds you at this moment. Electromagnetic waves from cellular networks pulse through your location at the speed of light. Wi-Fi signals oscillate at 5 GHz, carrying internet data through your home or office. FM radio stations broadcast at frequencies around 100 MHz. Television signals, GPS transmissions, satellite communications, radar pulses, all fill the electromagnetic spectrum simultaneously. You swim through this ocean of radiation, completely unaware of it. Human eyes detect only the narrow visible spectrum from 400 to 750 trillion cycles per second. But electromagnetic waves at every other frequency pass through you continuously. Radio waves penetrate your body without resistance. Microwaves cook food by exciting water molecules, but at the power levels used for communication, they pass harmlessly through tissue. The electromagnetic spectrum has become humanity's most valuable resource. Modern civilization would collapse without it. Every smartphone, conversation, every internet connection, every GPS navigation, every satellite broadcast depends on electromagnetic waves traveling at light speed through space and atmosphere. We have wrapped our planet in an electromagnetic cocoon, filling the spectrum with signals carrying information at rates exceeding billions of bits per second. Yet all of this emerged from Maxwell's mathematical insight in the 1860s. He predicted invisible waves based on equation symmetry. He calculated their speed from electromagnetic constants. He unified light with electricity and magnetism through pure theoretical reasoning. And from that mathematical foundation, built on nothing but equations and physical intuition, an entire civilization-transforming technology emerged. Hertz made the waves manifest in his laboratory, generating and detecting radiation at frequencies of 50 million cycles per second. Today's Wi-Fi routers operate at 5 billion cycles per second, 100 times faster. Modern electronics oscillate at frequencies Hertz could not have imagined generating, yet the principles remain unchanged. Oscillating charges create electromagnetic waves. These waves propagate at light speed. Antennas detect them through induced currents. Maxwell's equations describe everything perfectly. The electromagnetic revolution continues accelerating. 5G cellular networks operate at frequencies up to 100 GHz, enabling data transmission rates exceeding 10 gigabits per second. Researchers explore terahertz frequencies, the region between microwave and infrared, seeking even higher communication capacities. The electromagnetic spectrum becomes increasingly crowded as humanity demands more bandwidth for more devices transmitting more information. We have transformed the invisible ocean Maxwell revealed into humanity's communication medium, our sensing tool, our navigation system, our information infrastructure. We have filled the spectrum with signals, carrying everything from casual text messages to critical emergency communications, from entertainment to scientific data, from personal conversations to global broadcasts. And yet, despite this electromagnetic saturation, most people remain unaware of the revolution surrounding them. We use smartphones without understanding the electromagnetic waves carrying our calls. We watch satellite television without comprehending how signals travel from orbit to our homes. We navigate with GPS without appreciating the electromagnetic timing precision required. Maxwell could not have imagined any of this. He worked in isolation at Glenlair Estate, manipulating equations to reveal theoretical predictions. Hertz demonstrated the waves in a small laboratory, never dreaming of practical applications. Yet their work unleashed a transformation that continues reshaping human existence. From Maxwell's 4 equations through Hertz's spark gaps to 5 billion smartphones, the electromagnetic revolution has connected humanity in ways unimaginable to previous generations. We communicate instantaneously across any distance. We access information from anywhere at any time. We coordinate activities globally through electromagnetic signals traveling at the speed of light. The invisible universe Maxwell revealed mathematically has become humanity's most essential infrastructure. The electromagnetic spectrum sustains modern civilization as fundamentally as agriculture sustained ancient societies. We have awakened to electromagnetic reality, learned to generate and detect waves across vast frequency ranges, and built our connected world upon the invisible radiation filling every cubic centimeter of space. Maxwell's legacy surrounds you at this very moment, pulsing through the air at light speed, carrying voices and data and images through the electromagnetic ocean that sustains our technological existence. Look upward on a clear night, far from city lights, and you see what appears to be darkness punctuated by points of light. But your eyes deceive you. The universe is not dark. It blazes with electromagnetic radiation at every frequency across the spectrum. You simply cannot see most of it. Human vision evolved to detect a narrow band of wavelengths, the frequencies where our sun's radiation peaks. But electromagnetic waves fill the cosmos at frequencies from nearly zero to beyond imagination, carrying energy and information across distances measured in billions of light years. The Sun, our closest star, demonstrates electromagnetic power on scales difficult to comprehend. Deep within its core, hydrogen nuclei fuse into helium under temperatures reaching 15 million degrees Celsius and pressures 250 billion times Earth's atmospheric pressure. This fusion converts mass directly into energy, according to Einstein's equation. Every second, the Sun transforms 4 million tons of matter into electromagnetic radiation. That radiation begins as gamma rays, the highest energy electromagnetic waves. But as it fights outward through the Sun's dense interior, it gets absorbed and re-emitted countless times, gradually shifting to longer wavelengths. By the time radiation reaches the Sun's surface, it has transformed primarily into visible light and infrared radiation. This journey from core to surface takes 170,000 years. Photons bouncing randomly through the solar interior before finally escaping into space. Once free, the electromagnetic waves travel outward at light speed. They cross the 93 million miles between Sun and Earth in 8 minutes and 19 seconds. Every square meter of Earth's surface receives about 1,360 watts of solar electromagnetic radiation when the Sun is directly overhead. This energy drives weather systems, powers photosynthesis, warms oceans, creates winds. All of Earth's climate, all life's energy except nuclear and geothermal, arrives as electromagnetic waves from the Sun. But the Sun represents just one ordinary star in a galaxy containing 200 billion stars. Each star generates electromagnetic radiation through fusion. Each broadcasts across the spectrum. And beyond our galaxy lie hundreds of billions of other galaxies, each containing billions of stars, all radiating electromagnetically. The universe blazes with electromagnetic energy at every frequency. Consider the cosmic microwave background, perhaps the most remarkable electromagnetic phenomenon in the universe. 13.8 billion years ago, the universe emerged from the Big Bang as an incredibly hot, dense plasma. For the first 380,000 years, This plasma was opaque to electromagnetic radiation. Photons could not travel freely but scattered constantly off charged particles. Then the universe cooled enough for electrons to combine with nuclei, forming neutral atoms. Suddenly, the universe became transparent. Photons that had been trapped in the primordial plasma were released, streaming freely through space. This moment, called recombination, occurred everywhere simultaneously throughout the universe. Those ancient photons still travel through space today. They have been stretched by cosmic expansion, shifted from visible and infrared wavelengths to microwave frequencies around 160 gigahertz. This cosmic microwave background radiation arrives from every direction, a faint electromagnetic glow filling the universe. When you tune a television to a channel with no station, about 1% of the static you see is caused by these ancient photons, electromagnetic messengers from the universe's birth. Astronomers have mapped this background radiation with extraordinary precision. It is almost perfectly uniform, the same temperature of 2.7 Kelvin in every direction. But tiny variations exist, temperature differences of 1 part in 100,000. These fluctuations represent density variations in the early universe that eventually grew into galaxies and galaxy clusters. We see the seeds of cosmic structure encoded in electromagnetic waves from 13.8 billion years ago. Pulsars provide another cosmic electromagnetic marvel. These are neutron stars, the collapsed cores of massive stars that exploded as supernovae. A neutron star packs more mass than the Sun into a sphere 20 kilometers across. Material is compressed to nuclear density, with 1 teaspoon weighing 4 billion tons, and many neutron stars spin rapidly, rotating up to 700 times per second. These spinning neutron stars possess enormously strong magnetic fields, trillions of times more powerful than Earth's field. Charged particles accelerate along the magnetic field lines, generating beams of electromagnetic radiation that sweep through space like lighthouse beacons. As the neutron star rotates, these beams sweep across Earth, and we detect regular pulses of electromagnetic radiation arriving with extraordinary precision. Some pulsars pulse every few seconds, others pulse hundreds of times per second. The Crab pulsar, remnant of a supernova observed by Chinese astronomers in 1054, pulses 30 times per second. It broadcasts electromagnetic radiation across the entire spectrum, from radio waves to gamma rays. The electromagnetic beacon has continued for nearly 1,000 years, powered by the neutron star's rotational energy, gradually decreasing as it radiates electromagnetic waves into space. These cosmic electromagnetic sources demonstrate that radiation exists everywhere in the universe at all frequencies. Radio waves from distant galaxies, microwaves from the cosmic background, infrared from cool dust clouds, visible light from stars, ultraviolet from hot young stars, X-rays from matter falling into black holes, gamma rays from supernovae and pulsars. The electromagnetic spectrum is filled with signals, carrying information about cosmic phenomena across billions of light years. But the most remarkable electromagnetic fact may be this: you yourself glow with electromagnetic radiation. Every object with temperature above absolute zero emits electromagnetic waves. The wavelength of peak emission depends on temperature. Hot objects like the Sun emit primarily visible light. Cooler objects emit infrared radiation. Your body temperature is approximately 310 Kelvin, 37 degrees Celsius. At this temperature, you radiate primarily in infrared wavelengths around 10 micrometers. You are literally luminous, glowing continuously with electromagnetic radiation. You cannot see this glow because human eyes evolved to detect visible light, not infrared, but thermal cameras reveal it clearly. In infrared vision, humans shine brightly against cooler backgrounds. This thermal radiation follows the same laws that govern the Sun's emission and the cosmic microwave background. Every object radiates electromagnetically according to its temperature. The universe is filled with objects at different temperatures, all glowing at different characteristic wavelengths. This creates the rich electromagnetic tapestry filling space at every frequency. Even the apparently empty space between stars contains electromagnetic radiation. The interstellar medium, thin gas averaging less than 1 atom per cubic centimeter, emits radio waves at specific frequencies. Hydrogen atoms in space emit electromagnetic radiation at 1420 MHz when electrons flip between energy states. Astronomers use this 21 centimeter radiation to map hydrogen throughout galaxies, revealing structure invisible to optical telescopes. Complex molecules floating in interstellar space also emit characteristic electromagnetic frequencies. Molecules like carbon monoxide, ammonia, and even simple organic compounds broadcast electromagnetic signatures revealing their presence in distant clouds. Radio telescopes detect these emissions, allowing astronomers to identify molecular species across the galaxy and measure their abundances. Some astronomical objects generate electromagnetic radiation through non-thermal processes. Active galactic nuclei, powered by supermassive black holes consuming matter, accelerate particles to nearly light speed. These particles spiral through magnetic fields, generating synchrotron radiation across enormous frequency ranges. A single active galaxy can outshine its entire galaxy's stellar population, radiating more electromagnetic energy than 200 billion suns across the spectrum from radio to gamma rays. Gravitational interactions can also produce electromagnetic radiation indirectly. When two black holes merge, they create gravitational waves, ripples in spacetime itself. But if matter surrounds these black holes, the gravitational dynamics also produce electromagnetic radiation. In August 2017, astronomers detected both gravitational waves and electromagnetic signals from merging neutron stars, witnessing the same event through completely different radiation types. This demonstrates an important point. The universe communicates through multiple channels. Gravitational waves carry information about massive object motions. Neutrinos, ghostly particles that barely interact with matter, stream from stellar cores. But electromagnetic radiation remains our primary window into cosmic phenomena. Nearly everything we know about the universe beyond our solar system arrived through electromagnetic waves detected by telescopes. Radio telescopes collect low-frequency electromagnetic radiation, revealing cool gas, pulsars, and active galaxies. Infrared telescopes detect warm dust and star-forming regions obscured by gas clouds. Optical telescopes capture visible light from stars and galaxies. Ultraviolet telescopes observe hot young stars and high-energy phenomena. X-ray telescopes study matter near black holes and neutron stars. Gamma-ray telescopes detect the most energetic events in the cosmos. Each frequency range provides unique information. Observing across the entire electromagnetic spectrum creates a complete picture of cosmic phenomena. A galaxy might appear ordinary in visible light, but blaze in infrared, from dust-obscured star formation, emit radio waves from pulsars and supernovae remnants to produce X-rays from a central supermassive black hole. Only by combining observations across all frequencies can we understand what is actually happening. The James Webb Space Telescope, launched in December 2021, observes primarily in infrared wavelengths. It can detect electromagnetic radiation from galaxies 13 billion light-years away, light that left those galaxies just 800 million years after the Big Bang. The telescope's instruments are so sensitive they can detect the warmth of a bumblebee at the distance of the Moon. They reveal the infrared glow of the universe's first galaxies. Their light stretched to infrared frequencies by cosmic expansion during its 13 billion-year journey to Earth. Every electromagnetic detection from distant objects represents light that traveled for vast durations. Light from the Sun took 8 minutes to arrive. Light from the nearest star beyond the Sun, Proxima Centauri, took 4.2 years. Light from the Andromeda Galaxy took 2.5 million years. Light from the most distant galaxies took over 13 billion years, arriving from when the universe was young and dramatically different. This means electromagnetic radiation allows us to see backward through time. Looking at distant objects, we observe them as they existed when their light began its journey toward us. We see the universe's history encoded in electromagnetic waves arriving from different distances. Nearby objects show recent conditions. Distant objects reveal ancient epochs. The electromagnetic spectrum is not just a communication medium but a time machine, carrying information about cosmic history across billions of years. Your connection to this cosmic electromagnetic symphony is direct and immediate. The same equations Maxwell wrote at Glenlair Estate describe the sun's radiation, the cosmic microwave background, pulsar beams, your infrared glow, and every other electromagnetic phenomenon in the universe. The laws governing electromagnetic waves in a laboratory apply identically across 13.8 billion light-years of space and time. When you feel sunlight warming your skin, you experience electromagnetic radiation from nuclear fusion occurring at the sun's core 170,000 years ago. Radiation that traveled 93 million miles in 8 minutes to deliver energy to your body. When astronomers detect cosmic microwave background radiation, they capture photons that began their journey 13.8 billion years ago, when the universe became transparent. Electromagnetic radiation connects everything. It is the carrier of light from distant stars, the warmth of sunlight, the signals in your smartphone, the glow of your own body heat. It fills every cubic centimeter of space at every frequency, carrying energy and information at the speed of light. It is the universe's most fundamental communication medium, operating identically from quantum scales to cosmic distances. Maxwell revealed this electromagnetic reality through mathematical reasoning. He showed that light was electromagnetic waves, that invisible radiation existed at all frequencies, that electric and magnetic fields propagated together at a calculable speed. From his 4 equations emerged complete understanding of electromagnetic phenomena across the entire universe. The cosmic electromagnetic symphony plays continuously, broadcasting from countless sources across every frequency. Pulsars beam, galaxies blaze, the cosmic background glows, stars shine, and you, listening to these words, glow too, radiating infrared light into the surrounding space. A luminous electromagnetic being swimming through an ocean of radiation that connects you to the entire cosmos through the laws Maxwell discovered in his Scottish study over 150 years ago. Maxwell's equations, written over 150 years ago in a Scottish estate far from centres of scientific power, remain as valid today as when he first derived them. They describe electromagnetic phenomena with perfect accuracy, from the smallest quantum scales to the largest cosmic distances. No correction has ever been needed. No exception has ever been found. They stand as one of physics' most complete and elegant achievements, 4 statements containing infinite implications. Modern technology pushes these equations into realms Maxwell could never have imagined. Quantum computers manipulate electromagnetic fields at temperatures approaching absolute zero, negative 273.15 degrees Celsius. At these extreme temperatures, matter exhibits quantum behaviors where particles exist in superpositions of states, neither here nor there, but somehow both until measured. Electromagnetic fields guide and control these quantum systems, storing information in quantum bits that can represent 0 and 1 simultaneously. These quantum computers may eventually solve problems impossible for classical machines. Drug discovery, materials design, cryptography, optimization challenges that would take conventional computers billions of years might be solved in hours through quantum calculation. And all of it depends on precisely controlling electromagnetic fields according to Maxwell's equations, using the same laws that describe radio waves and sunlight to manipulate quantum states. The James Webb Space Telescope represents another frontier, where Maxwell's equations guide exploration. Launched in December 2021 to orbit 1.5 million kilometers from Earth, the telescope's instruments detect infrared electromagnetic radiation from the universe's earliest galaxies. Its primary mirror, 6.5 meters across and composed of 18 gold-plated beryllium segments, collects infrared light that traveled over 13 billion years to reach us. The telescope operates at temperatures around 50 Kelvin, cold enough that its own thermal radiation does not overwhelm the faint infrared signals from distant galaxies. Its detectors sense individual infrared photons, electromagnetic waves arriving after journeys spanning most of cosmic history. Every image reveals electromagnetic radiation from epochs when the universe was young, when the first stars were forming, when galaxies were beginning to take shape. These observations probe fundamental questions about cosmic origins. How did the first stars form? When did galaxies begin assembling? What physical processes drove the universe's evolution from nearly uniform early conditions to the rich structure we observe today? The answers arrive encoded in electromagnetic radiation, analyzed using instruments designed according to Maxwell's electromagnetic theory. On Earth, researchers chase one of physics' greatest remaining challenges: controlled fusion power. The sun's energy comes from hydrogen nuclei fusing into helium, releasing enormous energy in the process. If humanity could replicate this reaction in controlled conditions, it would provide effectively limitless clean energy. But achieving fusion requires heating hydrogen to temperatures exceeding 100 million degrees Celsius, 10 times hotter than the sun's core. No physical container can withstand such temperatures. The solution involves electromagnetic fields. Powerful magnetic fields, 10,000 times stronger than Earth's magnetic field, confine the superheated plasma, preventing it from touching container walls. The charged particles, in the plasma spiral along magnetic field lines, trapped within electromagnetic bottles called tokamaks or stellarators. This confinement depends entirely on Maxwell's equations, describing how electromagnetic fields interact with moving charges. The fields must be precisely shaped and controlled. Any instability, any deviation from optimal configuration, and the plasma escapes confinement, striking walls and cooling instantly. Researchers have worked for decades to solve this challenge, designing magnetic configurations that can maintain stable plasma confinement long enough for fusion reactions to become self-sustaining. Several experimental reactors have achieved brief fusion reactions, but sustained energy-producing fusion remains just beyond current capabilities. When achieved, it will represent humanity's mastery of electromagnetic confinement, using Maxwell's laws to cage matter at stellar temperatures and extract fusion power. The same equations that describe compass needles and radio waves will enable controlled stellar power on Earth. Beyond Earth, electromagnetic applications extend to space exploration's future. Mars missions face a fundamental challenge. The planet lacks a protective magnetic field. Without electromagnetic shielding, solar wind gradually strips away any atmosphere. Ancient Mars possessed a thicker atmosphere and liquid water on its surface, but lost its magnetic field billions of ago when its core cooled. Solar wind eroded the atmosphere over geological time, transforming Mars into the cold desert we observe today. Future Mars colonies might require artificial magnetic shields. Engineers envision placing satellites at Mars's L1 Lagrange point, the gravitationally stable position between Mars and the Sun. These satellites would generate powerful magnetic fields, creating an artificial magnetosphere deflecting solar wind around the planet. The electromagnetic shield would allow Mars's atmosphere to thicken over centuries, potentially enabling liquid water to persist on the surface again. This remains speculative engineering, but the physics is straightforward application of Maxwell's equations. Generate sufficiently strong electromagnetic fields, and they deflect charged particle streams. The same principles protecting Earth's atmosphere could protect Mars, implemented through human-engineered electromagnetic technology operating in space. The search for extraterrestrial intelligence represents another frontier where electromagnetic radiation plays the central role. Since 1960, radio telescopes have monitored specific frequencies, listening for artificial signals from other civilizations. The search for extraterrestrial intelligence scans billions of radio frequencies, searching for patterns that natural processes could not produce. Why focus on electromagnetic radiation? Because it travels at light speed, the fastest possible information carrier. Any sufficiently advanced civilization attempting interstellar communication would likely use electromagnetic waves, and certain frequencies are particularly interesting. The frequency of hydrogen's 21 centimeter emission line, 1420 MHz, represents a universal constant. Any civilization understanding radio astronomy would recognize this frequency's significance. So far, no confirmed extraterrestrial signals have been detected, but the search continues, scanning millions of stars across multiple frequencies. Every electromagnetic signal arriving from space is analyzed, looking for the patterns that would indicate intelligent origin. If we ever detect such a signal, it will arrive as electromagnetic waves traveling at light speed, perhaps from civilizations thousands of light years distant. Their message encoded in frequencies Maxwell's equations describe perfectly. Consider how completely electromagnetic understanding has transformed from Maxwell's time to ours. In 1865, electromagnetic waves were mathematical predictions. By 1900, radio existed, but remained limited to short-range communications. By 2000, electromagnetic technology had become civilization's foundation, and today, humanity contemplates electromagnetic applications from quantum computing to fusion power to interstellar communication. Yet Maxwell's four equations remain unchanged. They required no modification for quantum mechanics, no adjustment for relativity, no correction for new discoveries. Einstein's relativity actually emerges naturally from Maxwell's equations, which inherently contain the principle that electromagnetic wave speed is constant for all observers. Quantum mechanics treats electromagnetic fields quantum mechanically, but the classical field equations remain perfectly valid at appropriate scales. This permanence is extraordinary. Most scientific theories eventually require revision or replacement as understanding deepens. Newton's laws were superseded by relativity and quantum mechanics. Classical thermodynamics was explained through statistical mechanics, but Maxwell's electromagnetic equations stand complete, requiring no fundamental revision despite 150 years of scientific advance. The reason lies in their mathematical structure. Maxwell didn't guess these equations or derive them purely from experimental data. He reasoned from fundamental symmetries and conservation laws, from the principle that nature operates through elegant mathematical relationships. His addition of displacement current came not from experiment, but from mathematical necessity, from the requirement that equations possess internal consistency and symmetry. This approach, deriving physical laws from mathematical principles, has guided theoretical physics ever since. Einstein sought geometric descriptions of gravity, reasoning that space-time itself must be curved. Quantum mechanics emerged from mathematical requirements for probability conservation and measurement consistency. String theory attempts to unify all forces through mathematical structures in higher dimensions. Maxwell pioneered this methodology, showing that pure mathematical reasoning, guided by aesthetic principles of symmetry and elegance, could reveal physical truths. His displacement current term added to make equations symmetric, predicted electromagnetic waves before anyone detected them. The mathematics was correct because nature operates mathematically, because the universe follows elegant equations whether humans observe their consequences or not. Standing in his study at Glenlair, manipulating equations describing electric and magnetic phenomena, Maxwell glimpsed something eternal. He saw that invisible fields filled all space, that these fields carried energy and momentum, that disturbances in these fields propagated as waves at calculable speed. He unified light with electromagnetism, predicted invisible radiation at all frequencies, described phenomena that would not be detected for decades. And he did this through mathematics alone, through the power of abstract reasoning guided by physical intuition. He needed no laboratory, no experimental apparatus, no observations beyond those already published by Faraday and others. He needed only equations, mathematical consistency, and willingness to follow logic wherever it led. The legacy extends beyond technology into fundamental understanding. Maxwell showed that reality contains more than what senses perceive. Invisible fields exist, carrying forces and energy. The electromagnetic spectrum extends infinitely beyond the visible octave. Mathematics describes nature more completely than direct observation ever could. Human minds can comprehend cosmic truths through abstract reasoning, can predict phenomena never observed, can see the invisible through the clarity of equations. Every smartphone in your pocket, every satellite orbiting overhead, every radio telescope scanning for distant signals, every technology dependent on electromagnetic waves exists because Maxwell trusted mathematics over intuition. He added a term to equations for symmetry's sake, followed the mathematical consequences, and revealed an invisible universe waiting for human discovery. His 4 equations describe electromagnetic reality, from quantum computers to cosmic radiation, from thermal glow of human bodies to pulsar beacons across thousands of light years, from fusion plasma confinement to potential electromagnetic shields for Mars. They guide searches for extraterrestrial intelligence and enable global communication networks. They remain humanity's most elegant and complete description of a fundamental force. Maxwell died at 48, never witnessing experimental proof of his greatest prediction. Hertz died at 36, never imagining practical applications of his detection, yet their work transformed civilization more profoundly than almost any other scientific achievement. The electromagnetic revolution continues accelerating, penetrating deeper into quantum realms and extending further into cosmic exploration, always guided by equations written over 150 years ago. The invisible universe Maxwell revealed surrounds you at this moment. Electromagnetic waves carrying these words to your ears. Radiation from your smartphone connecting you to global networks. GPS signals from satellites orbiting overhead. Radio waves from distant galaxies crossing billions of light years. Your own infrared glow radiating into surrounding space. All described perfectly by 4 elegant equations. All manifestations of electromagnetic fields that Maxwell showed were fundamental to physical reality. From a 14-year-old boy prevented from presenting his own paper to the Royal Society, through decades of revolutionary thinking often dismissed by establishment scientists, to death, without confirmation of his greatest prediction, Maxwell's journey embodied determination against dismissal. He trusted mathematics when others demanded experimental proof. He followed equations to seemingly impossible conclusions. He unified separate phenomena into coherent theory. He predicted the invisible and described it quantitatively before anyone detected it. The electromagnetic spectrum he revealed mathematically continues yielding discoveries. Each new technology, each novel application, each deeper understanding of electromagnetic phenomena confirms that Maxwell saw truly. His equations were not approximations or provisional descriptions, but exact statements about nature's fundamental operations. They will remain valid as long as the universe exists, guiding exploration and enabling technologies Maxwell could never have imagined. The story began with invisible forces, with electromagnetic fields filling space undetected by human senses. It ends with complete understanding, mathematical description, technological mastery spanning from quantum scales to cosmic distances. Maxwell opened our eyes to the invisible universe, showed us that reality extends far beyond direct perception, demonstrated that human minds can comprehend truths invisible to human senses. His infinite legacy is not just equations or technologies, but a profound lesson about discovery itself. Trust mathematics, follow symmetry, seek elegance, and you may reveal truths about the universe that no instrument can detect, but that every experiment will confirm. The electromagnetic universe was always there, surrounding humanity throughout history. Maxwell simply showed us how to see it, and in seeing, we transformed our world and reached toward the stars.